Hello, and welcome back to another Binary Ninja stream. My name's Kyle, and I'm one of the instructors for Reverse this year. I'm teaching the Automated Reverse Engineering class. But today, we also have another one of our instructors who will be joining us to show off some awesome things that he'll be showing off a little bit during class, Brandon Miller. So thank you for
Hi.
coming on, Brandon.
Yeah, thanks for having me.
So do you mind telling us a little bit about what your class is going to be covering and maybe a little bit about what you're going to be showing off today?
Yeah, sure. Yeah, so I'm teaching the firmware reverse engineering course at Reverse, and so it's going to be heavily focused on binaries that run bare metal. So we're going to deal a lot with microcontroller programs, real-time operating systems, bootloaders, UEFI firmware, baseband, and we're going to get into how that code interacts with memory mapped I/O and a little bit into VR, as well as uh, teach some tricks for specific to firmware reverse engineering when dealing with things like raw binaries and lack of information that you can leverage for symbols or whatever it may be that makes reverse engineering raw binaries more challenging. As well as then we're going to get into more advanced topics of architecture development and some automated scripting as well.
Awesome. You named a lot of different features there, like memory mapped I/O, writing architectures. How does reversing firmware differ than reversing normal userland binaries, and why do you need to maybe be able to write your own architecture plugins for Binja?
Yeah, so I mean, it all varies based on the architecture, but at the foundation, I guess one of the most common problem sets um, is oftentimes you're dealt with raw binaries, binaries that aren't ELF or PE or have a file format that describe the sections or the memory map, where code is versus where's data, as well as uh, on microcontrollers, you deal with things like interrupts and interrupt service routines and hardware interrupts for software interrupts and all of the different um, challenges with control flow. And that's just strictly speaking the less exotic architectures such as ARM, for example. But then you get into DSPs and now you have very complex pipelines. You have parallel instructions, and so we're going to cover some of the more advanced features that some of the more advanced APIs in our architecture class that can be leveraged to model some of these complex pipelines.
Sweet. I'm not going to keep us in the interview portion for too long because I'm really excited to see your demo today. Is it okay if I switch to your screen? All right, cool. So what are we looking at here?
Yeah, so one of the things that we're going to play with in class is a couple Meshtastic devices. So for those who are unfamiliar with Meshtastic, the way it works is um, Meshtastic, Meshtastic devices are more or less LoRa radios that also have a Bluetooth interface. So you can connect either over Bluetooth over serial, um, a phone or a laptop, and it basically bridges it, for text messaging primarily, as well as data transfer between two end devices such as a laptop or a phone, and then this mesh communicates over LoRa, so your messages can travel multiple hops to reach the intended destination. Now in class, I've written some custom firmware that's more or less just a fork of the Meshtastic upstream with some features. But in doing so, naturally, I was curious, and I knew there's a lot of research, especially around DEF CON, done on the resiliency to of these protocols, specifically focusing on protocol attacks. And I know at DEF CON, I think they had the largest known Meshtastic network
Mm.
that consisted of over 2,000 nodes. I know there was a talk done
Yeah,
and
there were some live maps
they
while we were
found.
there too that were interesting to watch.
Yeah, yeah, that's right. You were there. From that, I know there were a lot of bugs patched,
Mm.
and a lot of good done for for the community. So this project, it started out, and it really is a hobbyist project. However, it's kind of grown since then, and I know like even countries like Taiwan are relying on it for off-grid
Oh wow.
communications in the event that they were invaded by China, for example. And so people are relying on this as a backup for no internet or no cell service.
So the
And it's also
integrity of these
used.
messages might be important, is what you're saying.
Oh, absolutely. Yep.
Okay.
Yep. Yeah. And the security of um, the protocols is, as far as the protocol design and the crypto is fairly well documented as well as its deficiencies.
Hmm.
Um, but I have honestly not spent too much time like source code auditing or anything like that. I was focused on just writing custom firmware for my class. But in doing so, naturally, I have two radios here, and looking at some of the code, I stumbled on a few design flaws that were fun to write some custom firmware on my end radio to see if I could, from a remote node, trigger some sort of undesired behavior. So yeah, so I mean, with me, I have two mesh LoRa Meshtastic radios. This one is connected um, from to my laptop over serial, and then this one pretend it's miles away.
Okay.
And the remote one, the one that's not connected, has some custom changes to trigger a design flaw in the iOS app or the macOS Swift app that's used to send messages. In order to find this, you kind of just had to understand the way the Swift app works as far as messaging and how it communicates over serial to the radio, how the radio then constructs a LoRa Meshtastic packet, sends it to the remote node, how acknowledgements work, and how um, to construct responses in firmware. So the way the remote node works is it has firmware in it that is looking for a specific message or really a specific pattern. So normally, like you would construct a message, you'd send it, and you can probably hear the beeping. It's been acknowledged, and then the firmware has code in it to auto respond.
Should I be showing your screen right now?
It should. Yep.
Okay. So we see contacts here. We've got yo and then hello coming back.
Yep. Yep. So I sent on the serial connected device, I sent that message, and then it went over LoRa, traveled to this device, and this device has firmware in it that just auto responds with hello under certain conditions. For demonstration, I have it just hard coded to trigger on yo to just respond normally. And so you can see as I send these messages, you'd see like similar to what you'd see when text messaging, a complete conversation here. Um, so now if I send anything other than yo, we'll send hi. Um, it's sending to the remote radio, and then you'll notice the sent message just disappeared.
Interesting. Very interesting.
So, so you could send these messages. It's responding, and the design flaw I noticed was in the app. It triggers on the mesh packets reply ID field for associating responses, um, or basically updating or adding emojis or whatever to these responses. So something that you can do, for example, is you can, uh, this is funny as well, apply an emoji to a message and wave, and you'll see it'll, when it responds,
Oh,
it replaced
interesting.
the emoji with the message that my remote node has sent. Um, so yeah, yeah, harmless, but fun little bug to play around
So
with.
wait, those reaction fields can be any text then?
Apparently,
That's
yeah, yeah,
really funny.
yeah.
I love
So
that.
yeah, not only that, like obviously the response from the remote node was not supposed to update your emoji that you
No.
added to the message.
No,
So
that's really amazing actually. It's kind of
yeah,
free
yeah.
threading. Can you do multiple reactions with text then?
I have not tried that.
Interesting. Very interesting.
As far as options to, yeah, tap back, you have these pre-canned emojis that you can use. Um, so yeah, but I mean overall, like in the little amount of time I've spent actually looking at the code, it's actually a really well designed project. I think a lot of the security flaws um, were discovered and as part of DEF CON as well as just it being a well-maintained project. But I did find a off by one error though that again is a harmless overflow. I don't think it's exploitable by any means, just because it writes into a padding section. It's into a struct region. So I was able to harness this and test that I could trigger this from a remote node.
Oh, interesting.
If I can find where it was.
So you just stumbled across these while you were working with it, or how'd you find some of these?
Yeah, yeah. So a lot of these yeah, yeah. This particular one I stumbled across from. Yeah, okay, clearly not. Yeah, yep. So this pattern to apply a bell character, which basically triggers the beep on the remote end. You'll
Okay.
notice right you'll notice right here it checks the payload the decoded.payload slide to see if it's less than the data payload length. So it does a bounds check here, and then it writes to the end of that. This write is safe. However, this
Mm,
second character that's written is not safe. This should actually be payload len -1.
hmm.
Um, so yeah, you can construct and overflow this buffer by 1 byte and get a null to write outside the bounds of that. Um, Another fun little bug I'll probably submit a PR for, but not exploitable. When you look at the um, the structure, because the payload buffer is 233 bytes. So then there's padding um, in the payload buffer that prevents it from writing to where anywhere useful for an attacker. But yeah, I think it's yeah. Okay. Yeah.
Do you
Yeah. This
expect
data
that?
T payload.
Okay.
This is a 233 byte protobuf byte array. So you notice right after that is the want response. So technically, if there weren't padding between these, um, there is. This isn't a packed structure, so um, you might be able to overwrite that want response. I don't think you could do anything useful, but maybe. Guess you wouldn't get a response. So yeah, I mean, this is 15 minutes of looking at the code as well as primarily just writing my custom fork for the class. But um, so yeah, I think there's still bugs to be found in it. A fun little protocol to look into. But yeah, other things I want to talk about as it pertains to the class is so this is the firmware that runs on the device on that particular Meshtastic radio.
Right.
So some of the things we're going to go over in class is for example, how code interacts with external hardware, specifically through memory mapped I/O, as well as over data buses and other things.
Before I let you get
Um,
into that, I just want to cover. You said you found that bug in like 15 minutes. So do you expect that people in the class will find similar bugs potentially during class?
Potentially. I mean, yeah, I'm sure there'll be a couple people way more well versed at VR than I am that stumble on some more bugs. Honestly, there's a lot of really good code in that firmware, a lot of good bounds checks. But I think a lot of the obvious mem copy, stir copy, base buffer overflows are uh, have been shored up, but I think some of the less obvious are still there to be had, specifically
Yeah, for
integer
that.
underflow, integer overflow type bugs that could lead to downstream overflows or anytime you're dealing with a protocol that has like TLV fields in it,
Hmm.
there's inevitably bugs to be had.
Yeah, that particular bug, it almost looks like we could write a signature for it where we're looking for arrays being indexed with a constant where like the dominating basic block has a condition that does a less than and not a less than and equal to or something.
Yeah, yep,
Those might be
y-
able to be scripted out.
yeah.
We also have a question here in chat about do you have any idea how the protocol prevents messages from being looped over the network? Because I think that they echo messages 3 times when they receive them, right?
Yeah. Do you mean just from like a third party? Like if you were to write custom firmware that were to
I guess this
um,
question's asking about the default firmware, um, how it, or if it's a protocol level, how does the protocol itself handle not just bouncing messages back and forth between two nodes forever?
so yeah, it does checks. It's got I, I might be misremembering, but it does have mechanisms that it triggers on specifically in the protobuf or in the Meshtastic packet, more or less. Specifically, there's a to and a from, as well as a randomly generated 4 byte um, ID for the message. And so once it gets a response
Mm,
um, to a message that's sent, it's able to associate using that ID.
hmm.
Now, in this case, in the case of that silly bug that I showed there, they should be doing more than just checking the reply ID and then keying on it to update the message in the window or in the
Hmm.
UI. They should also probably check the from to make sure it's not coming from a remote. Um, because yeah, the Swift code is also open source, and you can see it's aware of its own ID,
Mm.
um, and so it very well could filter that out.
Oh, yeah, that makes sense.
Yeah, but also as far as continuing to repeat messages, I believe that all the messages in the Meshtastic protocol are ACK. So when you send something, it'll get an ACK back,
Okay.
and um, before it moves on.
That's interesting. Yeah. So when you send a message, it goes to whoever is in range, and then they all act back. They send it to all their nodes, but if a node presumably sees a message has seen and sent before, it's not going to repeat it.
Yeah, yeah. On the mesh front, I'm not sure exactly how like multiple hops works,
Right.
for example. I don't know if every node acknowledges every packet that goes out. It
Hmm.
seems like it'd be fairly busy. Um, However, it might be how it has to work.
I mean, yeah, it could also just race to whoever acts first, and whoever catches that act cancels their own. But That's interesting. I didn't mean to cut you off there about the memory maps I/O you were going to talk about though, or the
Yeah,
social
yeah,
registers.
yeah. No, just some of the things we're going to go over is how uh, excuse me, code that's running bare metal on a microcontroller, how it interacts with external hardware through memory mapped I/O and hardware mapped registers. So in this case, this is the firmware that's running on. This is the clean upstream firmware that's running on the WIO tracker I have in front of me. And I believe the board is a NRF 52840. So in this tab is Firmware Ninja. It's a sidebar plugin that comes with Binary Ninja Ultimate. And it has a lot of features specifically for searching and finding code patterns of code that could be interacting with memory mapped I/O or just SRAM regions that aren't backed by the file. It looks for patterns in code for like bit banging or just like a busy loop on a like an outside region. In the case of this binary, um, I used our SVD loader to load the SVD file for this board. So you can see that you get nice annotations and sections and segments created for these memory mapped I/O regions. Um, so normally when you're reversing code that runs on a microcontroller, if you're lucky, you have access to the data sheet. Um, and you're looking through the data sheet and you're looking at the hardware, you're looking at the pins, you're trying to identify what's connected to what pins, where the traces go on the board. In the case of this device and this firmware, it uses a pulse width modulation um, device for emitting tones, specifically the beeps. So um, if you're reading the data sheet, it'll tell you really what this similar information that the SVD provides that we've loaded, and specifically like the enables the PWM device as well as there are other pins to control it. So we're going to go through how to use Firmware Ninja to identify these patterns and to filter down to devices that you care about and to find the code that's interacting with those devices, and as well as finding code that indirectly accesses those devices. So, for example, one of the features in Firmware Ninja, you can go to the PWM2 enable um, and highlight it, and then we have this button that will show the reference tree. Um, and this kind of graph can get messy depending on how many layers, but you can see that the stop playback function directly interacts with this register. That function contains the code, the instructions that are reading or writing to this register. Um, and it obviously shows you that it's in this case it's writing to the register. Um, and if you this is kind of meant to be similar. Think of it as like a call tree, but I call it a reference tree, and in that it not only contains function calls, it also if there are data variables that contain function pointers to those functions, those are also included in the tree, and that's important because a lot of microcontroller programs have interrupt vector tables, and in those interrupt vector tables, you have pointers to interrupt service routines. And if you just included call trees, you may not understand that that hardware is interacted with during an interrupt. Um,
Okay, so just to make sure I have this right, you've got you've already run the memory insights on this, so you've identified where the I/O devices are. You've selected one of them in the Firmware Ninja sidebar, which is showing you the reference tree for it. We can see that it is being written to in that column, but then down below we also see that that's the specific function that's writing to it. And then what is tone to that function?
so tone calls stop playback, and
Oh,
Arduino hardware abstraction layer function tone calls tone. And then also you see these different play tones. So, you could start understanding the code um, and how um, the code is driving that PWM.
So that
Um,
PWM device, that's the leaf of this tree, the leaves of this tree, all the things that eventually flow into it, right into it.
yeah,
Okay,
yep, yep.
very interesting.
So yeah, yeah. I mean, obviously, oftentimes firmware, just like any other code, contains like a hardware abstraction layer, some sort of interface that interacts directly with the hardware. But usually, that's not what you care about as a reverse engineer. You care about, the higher level functions that are constructing messages um, or doing something with the
Right,
hardware.
right.
So um, so yeah, memory insights helps boil that down.
That's really cool.
Um,
Yeah.
so the other thing we're going to get into is some of the more complex DSP pipelines, and specifically show how some of the new APIs we've added to our architecture class allows for modeling some of these complex pipelines. So even going like Hexagon is a architecture we added recently in Binary Ninja. And Hexagon, if you look at the disassembly, you can see these brackets and these instructions within these brackets. These represent instruction packets, and within these instruction packets, these instructions execute in parallel. So now you have these some of these instructions where um, you can't just lift them in order. You have to handle the entire instruction packet at once. For example, in an instruction packet, you could have, it shouldn't take me a while to find one, you could have a jump that's the first instruction in the packet, and then followed by a move. And that, if you just lift those instructions in order, um, the jump is going to take place first.
Mm-hmm.
Or yeah, here's a perfect example. This instruction packet right here. You see if P0 jump to this location. Um, if I
And then
go
the second
to,
instruction's a conditional move, a conditional
yep, and then
move.
that second construction is a conditional move. So if you just lifted these in order using our normal um, instruction at a time, just get instruction low level IL, you're going to lift this as a jump, and then this instruction is never going to execute. So you can
Mm.
see in our lifted IL
Mm-hmm.
that, if I can go back to where that was, um, that we first lift so we reorder these instructions when lifting. And we lift the conditional move first, and then the jump after that. So in some cases, though, you can't reorder.
But we
And
only
and
reorder them in the lifted IL. We're showing them faithfully in the disassembly.
yep, yeah, yeah. So the assembly is byte for byte how the instruction or how the program's machine code um, is represented.
I'm noticing that it will assign a register. I assume P0 is a register, but then it's also using the new version of it.
Yeah, so Hexagon has what's called .new semantics. So in this particular instruction, it's saying so P0, and then this is a compound instruction. So in 4 bytes, you have almost two instructions. But yeah, P0 equals, so it's setting this predicate register, and then the .new means that the DSP needs to use the new value of P0 instead of the old value that's in the register file. Um, so in other cases, like you might have P0 equals compare, and that updates P0, and then like an if P0 without the dot new, and that means you have to use the old value of P0 prior to this instruction packet executing.
Yeah, I would have assumed that in a packet you only have access to the old versions. My understanding about Hexagon is the reason they do this packet stuff is to simplify their pipeline so that it can be a low power device. So the fact that it still has data flow constraints within parallel packets is very interesting to me.
Yeah, I mean it's low power is one thing, but it's also
Hmm.
just so these instructions can execute very fast.
Okay.
So if you can give four instructions that execute simultaneously in different slots, so like that's where DSPs kind of excel. Um, so there are constraints though on what instructions can run in what slots and things that we can rely on a little bit to
But the
um,
compiler guarantees that you'll have the new version of P0 by the time you want to use it in this for later in this packet, I assume.
Uh, not the, I mean, yeah, the compiler obviously the instruction encoding tells the DSP that it needs to use the new value of P0
Do you
at
know
this
if that'll
instruction.
result in stalls in any circumstances? Or
There are like, yeah, there are certain constraints surrounding these instruction packets. So like for example, like in the instruction encoding, the this p0.new, like the register is not encoded in this instruction.
oh,
It
okay.
actually tells you the way the instruction bits uh, model that is it tells you what slot to consume the produced value from. So in this case, this packet encoding says like consume the produced value or the destination register of
Interesting.
slot zero.
Very interesting.
So, this is another case where you can't just decode this, you can't even disassemble this instruction without processing this whole packet.
Yeah, that's very interesting. Okay.
So if I go, for example, something I'm working on currently, TMS 320C6000, and it gets even more complex. So TMS TMS 320C6000, um, its pipeline, the way it works is certain instructions take multiple cycles to execute, not number of like so
Right.
they call them delay slots, but they are not like delay slots in MIPS or PowerPC where they're
Okay.
all instructions based. Um, they're cycles based, and certain instructions take more cycles to execute than others. And so, for example, this branch right here is a branch to memcopy.
Okay.
However, the branches take 5 cycles before PC is updated.
Interesting.
So the branch actually doesn't occur if you look at our lifted IL until after this NOP. So, and then loads take, I believe, 5 cycles, maybe four, um, before the destination register in the register file before its value is populated. So
There's a
you
lot going
have,
on that line that is very interesting to me.
yeah, yeah. So now you have this case where this branch, it's executed here. But we don't lift it here. We lift the effect. It's actually in 2 stages. The way or well, the branch is in 1 stage, but the load's actually in 2 stages. And in the ISO or the programming manual, it tells you that after 3 cycles, A3, the value is basically loaded into a temp register when lifting. But
Okay.
then after 5 cycles completes, then that value in the temp register is available in the register file. So that's why you see when lifting it that the load takes place for one after the add. It's loading to a temp file, and then you can see an instruction later um, that temp value is loaded into A6. That's when it becomes available actually in A6.
Oh, that's
Um,
really
so
interesting. Okay.
yeah, so you can see like high level IL, this instruction um, or these instructions are just doing this. It's just a call to mem copy
That's really
with
cool.
these values.
For the uninitiated, including myself, would you mind walking through a little bit of the syntax and the assembly there? What are the dot postfixes and What is star plus A3?
Yeah, so star plus the dot prefixes are the slots that the instructions are executing on. So you have L slots, you have D slots, and certain instructions can only run in certain slots. So like ALU instructions or others can only run in certain slots. So there are constraints like that. We can actually leverage these to identify like if an execute packet is valid.
Interesting.
These two pipes signify that these two instructions are part of the same execute packet, meaning they're executed in parallel.
Right.
And that's not saying they complete in parallel. That's their execution is kicked off in parallel. Like I said, this branch takes multiple cycles before it completes. The add executes in one cycle.
And when you say that that postfix is saying what slot to put it in, is that effectively different pipelines on the processor? So one of those is running in the L pipeline and one of those is running in the S pipeline simultaneously?
Yeah, more or less. I Once we get into hardware, I cap out.
Sure, 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 sure. But do can we envision like the L things and the D things and the S things happening separate from each other, or do they still all
Oh
share the
yeah,
same?
yeah. They are executing in parallel in the case of execute packets.
Okay, very
So like
interesting.
for example, you're not going to see dot S1 and then double pipe dot S1.
Right,
Now
okay.
you have two instructions in the same slot. So there are constraints like that. Um, and also like these DSP architectures are funky in that like C6000 doesn't have a dedicated global move instruction. So these absolute value instructions are actually just being used as moves.
Oh, that's funny. That's really funny.
And then not only that, if you notice, there's no call instructions in C6000. So
Yeah, is that a branch?
um, yeah, everything's a branch. You have branch or bnop, which is branch with nop. Um, and so you have to figure out things like what's a call, what's a jump, and what is
Mm-hmm.
a return.
Mm-hmm.
Thankfully, they were consistent about using B3 as the link register. So, so there's a lot of analysis that needs to be done at the control flow recovery stage as well as the function lifting stage. So, and really, like what I'm demonstrating here and what I'm leveraging here is we added a few new APIs to
Yeah,
our architecture class. One of which is lift function. So
of course.
previously, where you just write your get instruction low level IL callback, and then our core function lifter would invoke that to lift an instruction at a time. Now you can override a function called lift function, and you can lift the entire function in one swoop. And that's what's ultimately required here.
Right.
In these core changes were required to even start development on C6000.
How far are you with TMS 320 C6000 at the moment?
Yeah, it's coming along. There's some contributions from the community. Shout out Endeavor for kind of propelling some of the development early on. And then I kind of had to take a hiatus to work on these core changes to add these new APIs, specifically lift function, get instruction low level IL, or get instruction text with context, and then analyze basic blocks was one that I added and needed for Hexagon. And now that I've got all that merged to dev, I've about a week ago I started writing the lifter. Um, so uh, yeah, it's coming along. There's still some hard problems that need to be solved, and I'm hoping uh, sometime uh, within a few weeks after Reverse that maybe I'll have something on the dev channel to try out.
I mean, that's pretty exciting to hear. It's taken you a week and you've already gotten this far. Do you mind showing the low level IL on the bottom again? I'm curious, how does it save, in this particular architecture, how does it save return addresses?
So on this one, this is a tail call, so
Okay.
it isn't. But uh, you know what? you guys can, I'll just show, let me switch over to this one, maybe.
I can also hide your screen for a minute if you'd like.
No, it's fine.
All
It's
right.
just uncompleted work. Let me see.
This architecture looks so bizarre. It
Yeah, it
looks like
is.
it's
Yeah.
doing most of the weird address stuff in the D pipeline.
Yeah, like a lot of the loads in stores
Mm-hmm.
are done in the D pipeline. Yeah, so stores are or loads are left to right to add more context, and that the star plus is saying to add um, the value of B6 to the base register when dereferencing um, for the
Okay.
for the store.
Right.
And then so like you also see like star plus plus, which is it'll like pre-increment the base register as well as use it to dereference. Or uh, like plus plus star, I think will like pre yeah, there's like pre-increment and post-increment and pre-decrement.
Of course,
So
naturally.
yeah, yeah, and that's well, and that's just DSPs in general. Like Hexagon has the same constructs.
Okay.
Um, so one of the things that makes them quick. This one clearly just tail calls as well. I'm just, but yeah, so really what you'd see is just a move to these move instructions. You'd see a combination of move K and move KH to B3, which is the link register, followed by a branch
Oh,
to
okay.
like the start of a function. And then you can see how the functions return. It is just a branch to B3.
Oh, okay, interesting. Very nice. That's cool to see.
So, yep. Yeah. So thankfully, the compilers are very consistent about um, uh, using B3 as the link register.
Um, Not to give anyone ideas, but would it break our lifting if they were to not use B3? How do you feel
No, it
about relying
shouldn't.
on heuristics?
Yeah, no, it shouldn't break it.
Mm-hmm.
It might make it harder to reverse though.
Right.
For example, like branches. Right now, I have it lifting branches to B3 as returns. Um,
Mm.
and but also like when one of the things it does is when it iterates through the basic blocks, it's able to track when B3 is updated, and that's how I'm able to tell whether or not a branch is a call versus a jump.
Oh, okay.
So if B3 isn't updated before the previous call, then it's a jump. And really like all this really affects is where the basic blocks go, right? What functions they're assigned to, and so yeah, it can make it more challenging to reverse, but it shouldn't break anything.
No, that's neat. That's very neat.
Um, yeah, and yeah, so that's kind of it that I have prepared. I could show other things, but I feel like I've talked long enough.
Well, yeah, no, I really appreciate that. It's exciting to see. I'll switch back to our faces. It's exciting to see two new architectures that we haven't shown off much on stream, and it's awesome to just hear you describe some of it. Since again, we haven't looked at it much, so going into some of that specific syntax is very helpful.
Good. Yeah.
All right. Well, I'll kick it off to the rest of the reversing we're going to be doing. And thank you for coming around. Round three tickets are on sale for reverse. Um, so get your tickets before those run out. I know that the room block is filling up, but you should still be able to get the discounts if you're thinking about coming. And there's plenty of room in Brandon's class and my class left if you want to sign up for those. Brandon, you can feel free just to exit out. Again, thank you for coming by. All right. So then, let me reset a little bit here. And we'll switch over to my screen. Um, all right. I can close out of this now. and we're all good. So, all right. Um, I wanted to show off some just more reversing. We did a C++ reversing stream a while back, and now I have a slightly harder challenge that we could work on. I also have some other fun ones which I might show off. Let me just get those up. Yeah, so here's the binary I was thinking about us looking at. I know that this is a C++ binary because there's some sort of vtable in it, but unfortunately this binary is stripped, so we'll have to do a lot of hard work ourselves. And then I have this binary as well we could look at. And now, if you've been in the CTF scene for a while, you might remember this one. It was a lot of, this one got a lot of attention when it happened. Let me just connect somewhere where I can run this. Because it is a Linux binary. Yeah. Um, there we go. All right. So this is a really cool one because it fully renders a 3D environment in your terminal. And then you can walk through it. You can go left, right. Oh, there was something that happened there. Immediately after entering, you hear a thunderous boom. The wall ceiling behind you collapses into a pile of rubble. You barely avoid the falling rock. Doesn't really seem like there was anything that happened behind us. Seems like we can still go back. But that does get triggered every time we go past. But then this is just a bit of a maze. We can reverse this binary to figure out how to get to the end of the maze. Or we can do some C++ stuff if we'd like. And then, that actually might not be true. Let me try. Test, test, test. Okay. I should be a bit louder now. All right, there we go. So we can reverse this one and explore the map. Let me guys know if you have thoughts about that. Otherwise, we'll do the C++ one instead and hit our heads against this for a while until we want to give up. In the meantime, I also made something for myself that I want to show off a little bit. I made this little plugin here, this change profiles button. This is neat just because for a while I've had my own personal settings that I like to have when I'm reverse engineering. A little bit of a smaller font. I moved some of the sidebars around, although looks like that got lost recently. And then it's just nice to be able to switch back to a presenting mode. You can see in there I also had some IDA and Ghidra profiles in case you have those as your preferred method of reversing. And it changes your key bindings and a couple other things for you as well. I believe that in the next release we're going to have something like this, where when you first start up, you'll be able to select if you want to use our default key bindings or something more familiar to what you're used to. And then this might be moved up to the little Benji head, and maybe we'll replace that with some different Benji icons you can select for different profiles. If you think this would be useful, let me know. Our new wizard branch. I don't know which test build that is. If you want to send it to me, I'm happy to show that off. I just want to hear any thoughts about it. If people would love this profile feature or if they'd never use it. Um, yeah, all right. And then I'll show off that test build in a second. You will notice though right now I have it so it re-clears my recents anytime I switch back, but easy enough to fix. Um, okay. We've got our Finder window. We've got this star binary. the C++. All right, so I imagine here we have a number of constructors, some number of constructors at least, for a number of different objects. We've got some vtables. These don't really give us any information off the bat. We have even more complicated things, menu command, create command, rename command. So we might be able to find out some information about these different, um, where these different commands are being run. If we look at our cross references, we can check out where they might be being used. It looks like it is referencing data and being referenced by data. Okay, operator delete, that makes sense for, I think I had delete selected. I might not have. But I imagine we'll stumble onto these when we need to find them. Yeah, it's interesting there how it's showing me that reference, but that's delete for edit command. Delete command is that same address. Okay, so there might be a bunch of references from that same address, it looks like, yeah. So maybe that's being used as the base of some virtual table and we're offsetting from there. But again, I'm sure we'll find out as we keep reversing. It looks like we also have a test build, so let's go grab that. We can use the new command palette, which I love, and we can go to our updates. If you are one of the select few, you will have test branches. And we can grab 103. If you don't see all of these here, there's a setting, show all versions. When you do that and you go back to your update channel, you get a lot more versions in this list. Yeah, test. In theory, you do at least. Let's just restart. I believe it fetches those once. Update channel. Yeah, it's fetching them now. Apparently there was an update for me to install. Test, and we want to do 103. This one here. Well, I don't need to update for latest on the test branch. But we do occasionally give people access to the test branches if we know that there's a feature that you've been looking out for or very active in the community, have a habit of giving us feedback. That's another instance. 9103. All right, if I clear my queue settings, this will make it so it's as though I've opened Binary Ninja for the first time. Hello, welcome to Binary Ninja. How would you get started? Ninja defaults, I'm familiar with a different tool. If I just click this, interesting, this is fine since I have my profiles thing. I can always go back to the last one. But that looks like it does nothing. Um, cool. It just leaves Binja at the defaults. If I clear my queue settings again and I restart, I have restart bound to F12. I'm familiar with another tool. Oh, this is neat. You have existing custom key bindings. Selecting a preset will back up and replace them. That's nice. Better than what I've got going. We'll set up the key bindings and UI to match your experience. Graph view preferred, feature map on top, cross references as a dialog. Key relay key bindings, linear preferred, feature map hidden, and types hidden by default. Interesting, I didn't know that. So let's go ahead and replace my settings, make it idle-like, and does it actually do it too? Oh, right, and replace my key binding. Restart. Okay, but not a light mode. I would have expected those to switch to a light mode. But then we've also moved some things over up here as tabs. So usually you get that what's new pop-up. It tells you all the new things in Binary Ninja. which is now a tab. I actually like it that way. Can't close it right now. And then a Learn the Basics tab. I like this too. Recent projects, learn the basics. Oh, we can't do left or right splits. It'd be nice. Oh, we can. There we go. I like this. I like this a lot. For whenever you open a new Binary Ninja version, for it to pop up like this, I think that's pretty clean. And then I believe some of this stuff was mostly stand-ins. So if you guys have thoughts on this, let us know. Feel free in chat or in DMs. But I like where this is going. I think this is a little cleaner than what we had. And it's certainly nice to be able to onboard people a little easier from the other major tools. Let me switch back to dev. Update channel, update to dev, latest, automatically download. Cool. I've also thought of like, we could put other things over here too. If we had, um, like learn the basics as a box above plugins or something. Um, but I don't think we need to maximize for information density on the new tab screen necessarily. I like leaving it just as this bunch of blank space. Yes, I will reset my profile. Absolutely. Bouncing, 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 updating, and there we go. Oh, and we also now have automatic crash reporting, which I am personally a big fan of. I know that one of our coworkers is going to be looking into these and seeing what types of crashes we most often have that people aren't reporting about, um, and see if we want to, I guess, expand this. No binary content or identifying information is included. Application plugin paths may contain your system username, of course, yeah. We're not looking to spy on you. We just don't want Binja to crash. Presenting. Sweet. Now I have my hotkeys back. Um. All right. So let's get back to Star. I believe that. So we were looking at. I still have it. Is this it? This is not it. But we were looking at a different binary a couple weeks ago called Zoo here. I even have our BNDB from last time. And this one had symbols. Um, yeah, here we were. This one had symbols. We were able to just create the different structures. We were able to name things. But one of the patterns we saw was that in constructors, the constructor always seemed to call another constructor. So in this instance, what I'm thinking might be a constructor with a this variable of a object that is, let's see, var b0 is there. We have a 8. I saw a 0 which gets used. Oh, we also have an A8 which gets used. So this is maybe only a 8-byte class of some sort, which seems small to me. But this does call another function, which calls another function, which calls another function. One of the interesting things I think particularly about this binary is if we open Tonto and we do a function, a full call graph, actually, and we close the stack over there. Let's get back to main. Um, we have these weird tree structures in the call tree which in zoo, I'm not sure we had. Well, let's go to the constructor. It would be interesting to learn, though, that that's just the pattern of a C++ constructor. So we have the pets. Pets is called by main, calls all the other functions here. If we go into the constructor for animal, we can see animal calls exactly one other function, which doesn't call anything else. So that's definitely a different pattern from what we're seeing here. It could be more advanced initialization. It could be any number of things. But it is different, which is important to note. So then, okay, we are creating a new data variable here, which is the same size as what I was suspecting maybe our class is. Let's go backwards. Let's start from this one, which obviously has a vtable. Um, Interesting. It still is constructing or passing this over here. Let's let's start applying some types and seeing what's going on. We could start from up here, we could start from what's going on below. There's also this one weird singleton function getting called at the top, which might be a nit. We can look into this. Okay, there is some interesting information that we can get by looking at this actually. It's creating a directory. Dir name, or like current directory maybe. But let's name that dir name. Um, that's going to be a character pointer here. A car star, dir name. Okay, so that's just being passed to another function. And I'll leave the call graph up for now. Let me close the overlays so you can see it a little bit better. Just so we can sort of have an idea of where in the binary relative to some of these other functions we are. Did I name this function, or was that function just named func to start with? This function was just named func to start which is interesting. And this is also calling the destructor for string. Does this take an argument? If I had to guess, this takes a pointer to the string it's destructing. Yeah, and then somewhere, this might be delete as well because it's a destructor. I think that this func might be a destructor for a string. So we've got the string, we've got, let's give this string. I don't want it with a dunder in front of it though, or an underscore in front of it. So then this is deleting something else, potentially, but we're also, aren't we returning from here? Yeah, we're initializing the directory name. We have some weird ret val, which looks like it's being potentially used multiple times as multiple different strings. Where does this exist? Is it on our stack? Um, Interesting. It's showing us the class for the string on var 78. And then I would imagine this is the string constructor here. Yeah, we're allocating stuff. So let's name this string. And this is going to take, oops, I hit U on that by mistake. Its parameter is going to be this, and is going to apparently return a string reference. Not really, it's Um, okay, maybe it is returning this. And it's taking a string, and then this inner function is also taking a string now. We don't need to reverse standard string, so we can ignore that. And then we do two interesting things to it before we actually delete it again. But I want to know what the value is going to be. Get env, we're getting some environment variable, which is also coming from this ret val. This, well, we know that this has got to be a string. So let's apply that type as well. Um, there we go. And then this is taking a pointer to a string. Std string pointer. Cool. arg1. It looks like arg1 is used. Um, these potentially, they're not characters, are they? I was hoping they were characters. Um, all right, so we might be getting to some interesting things over here that are being applied to the string. Um, and then this too. mdata plus, mp. I don't know what these fields of a string are. We can look them up though. Go to string. A string is the alloc, the allocator, the string type, and then either a buffer for the string or a capacity for the string. So I'm guessing that allocator actually holds the string itself, and then perhaps this. Yeah, okay, and then this is the actual pointer to the string. So this is getting an environment variable based off of this function call with the pointer to the string in it. Do we think that this is a string constructor as well? I don't think this is a string constructor. I think this is something else. Um, okay. And yes, you can have spaces and symbol names. That'll just help me remember that I don't think it's a string constructor. Here we're doing some interesting stuff. I'm seeing an XOR and a loop based off of some call to a function, which is doing some weird math, including potentially an array here. So we're definitely going to be interested in what's going on here. Is this a de-optimized division potentially? arg1 times this number. One of the tricks I like to do is if the math is too hard to read through in a function, don't bother. We can set a user variable value to a constant value and just see, what if it's 0? Then in that case, we're setting RIX to 0. What if it'd be nice if we could double click a part of this and edit it. Um, I forget how to edit it. Otherwise, set user variable value. So that's if it's 0, if it's 1, it gets set to BC8F. And then if it's 2, I think it gets set to 2 times that. Say user variable value, constant value, 2. We're given this number. So that number versus this number. Um, It's not simply a multiplication. It's probably some weird math. Oh, it is. It's just that in decimal. Okay, so or this is just gonna be all of this for some reason is just times n. I could type and not name. Name. Okay, we'll name this n. Um, and then yeah, it doesn't seem like we need to think through the rest of this math. We just know that if n is 0, it's 0. If it's 1, it's that number. If it's 2, it's that number times 2. If we really want to check, we can look at it when it's 3, but I'm pretty sure it's going to be um, 3. Yeah, okay, cool. Sweet. That's a nice trick that we can always do so we don't have to read math. I was inspired by the um, yeah, I was inspired by Shusheng showing off the replay the time travel debugger because you can just be after a function and then go before a function, and you can see how the arguments are transformed through the function without having to actually reverse it. So for whatever reason, again, this is just some weird number multiplied by 2. I love that it's actually naming the output variable there, and it looks like we need an underscore for that as well. And now this, okay, so we're getting the address of something plus a offset that's changing. Oh, okay. This math is actually becoming rather easy. Is this an array on our stack? Var 30 plus I. We're dereferencing that. Okay, so this is definitely going way past the end of our stack. Um, we'll call that a void star. Or void star star. Not a triple star. Ah, it's not a function type. Thank you. Okay. So none of my types for this are getting that to actually look like an array. If I just do a array of 10, let's say, for giggles. Um, okay, so we're definitely setting it to 0 to start. If that gets set to 0 and then we immediately dereference it, how does this not crash? Um, I had a render layer on there annotating the call parameters here, which I didn't realize I had. That's actually really nice that it's showing you this is just a call, this is an argument for the call down here, just above it, because it's a loop. Um, this is a weird binary. This was a CTF binary, and I do believe it was adversarially crafted. So it's understandable that these patterns are not the most obvious patterns in the world. Um, okay, but it looks like we have maybe some data element that's going to be that large and an array of them. Um, so I think we can just come back to that. Um, init, weird, large. I think it's stack array. Yeah, it's definitely something on our stack. And maybe it's initializing it, maybe it's doing something else. We could run it under the debugger and see what's going on in each loop, but I'll hold off on that for now. Um, Mostly because I don't have a remote debug session all configured. And then let's make this just 8 bytes. What did that change? Oh, whether we return a result or not. And this is also returning, what is this returning? All of the result, if it's returning anything at all. And it is, because we use that number in not the string constructor to pass it to this, which allocates the data for the argument, and then probably, I would guess copies it over. We've got arg2 here, copy characters. Yeah, so I'm gonna guess that this is move, string move or string copy. We'll call it move for now. I'm hitting the wrong button. N, string move, and it needs maybe backticks. Nope, doesn't need backticks because I keep hitting type. I also need to turn on keycaster for you guys. Cool. Now you can see what I'm typing. So N, and we've got string move. All right. Maybe. Let's annotate that we're not completely sure by adding a question mark there. And then it looks like this is initialize this weird large stack array, which might be interacting with the stack of this function. And then move the result of that into arg1. So where were we? Back here. Who calls you? Actually, we can see that on the right. This function, if this is still working. What address are we at? 5230. It's not being shown in this graph. Full call graph. Okay. So it calls this thing, and it's only called by this init. So let's call this maybe decrypt and init string. And we'll go back to init. So we decrypt and init some string, which we need to do more analysis on, so we'll come back to it. I like to make assumptions, move on quickly, come back to them if we need to, if we discover that um, we were wrong. And then this is somehow getting an environment variable that's specified in that string. Um, and again, if we wanted to figure out exactly what this data was, I'd run this under a debugger and go from there. Is this, this is also interesting. So this takes a couple different data variables. How big is this? 118, 110, 108. So they're all within 16-inch bytes of each other. All right, so we might have move. We might have move again. Who calls this function? A bunch of people call this function. This is not just some weird one-off thing. This function calls, well, doesn't super matter, but it's called by this function, this function. I actually didn't know that the keyboard navigation works so well in .do. This is really cool. So I'm looking at a function on the right here, this oxbc8fn, 8f times n, and I'm just hitting left and right, and it's showing me the function that's calling this function on the left. And they all look very similar. We have n defined at the top, which I missed before, so that's going to be how this isn't crashing immediately. Um, they all have the same value of n. They start with I, which is 0. They set up their stack. Some of them are, then they're all initializing some other variables on their stack. Then they Okay, then they call this loop some number of times, up to 10, and each time they do that, they're setting their weird stack variable plus I. Hmm, okay, to this thing. arg1 getting the data at, oh, okay, yeah, it's just taking the byte at that and based on this math, XORing it. Yeah, okay. So I am starting to wonder if this is a rand or something that we've stumbled upon. And this is you're getting a bunch of different random values, but almost certainly not. This is almost certainly, if we display this as different bases, it's not obviously anything to me. It's not a floating point number. It's close to a nice round number in decimal. It's close to 2,006,000, or yeah, 2,006,000, 7,000. But that's not like a clean number. It's probably a size of something or any number of things. This still looks like an array access to me, where we're setting each byte to something based on the arguments coming into it. It's interesting that this version has an arg1 that does not get used, and then an arg2 which is getting used. Oh no, arg1 does get used. It gets passed to this, which is also something weird. It's swapping the result. So hold on. Is it using the result of this function? This function is getting referenced by this function. This is the only place it's called. So this does not actually have a return value. Okay. So we can make that void. And then what it actually is doing is the first 4 bytes of arg1. No. So it's setting the data at arg1 to be the data at arg2, and then the first 4 bytes of arg1 become the first 4 bytes of what arg2 was. It was more like a 4-byte character array than a number. Oh, and so is this. Oh, but these are 128 byte pointers? Hello, didn't notice that. Um, so we got floating point in here too. That's exciting. So it's a good thing I checked out those other numbers in floating point. Um, okay, so keeping in mind that these are 128 byte numbers, or potentially just 16 byte data buffers, and it's doing some crazy optimization stuff. Let's make this now. If I made this a character array of 16 and a pointer to it, will it let me do that? Is there a way to specify that? Not a array of 16 character pointers. Um, no. Um, hmm. This doesn't look better. This looks worse. So I'm not doing that right at all. But that's okay. We're loading. What's confusing here is we've got arg2 and we're accessing it like an array. Um, we're getting the address of it, and I don't know how arguments work when they're registers. Oh, right, they're passed on the stack when they're that big. So we are reading 8 bytes from RSI or 16 bytes from RSI into ZMM, and then we are getting the 4 bytes after that into EAX, and then we are copying those 16 bytes into the other one, and then we're overwriting the 4 bytes after it. This is very strange. This is very bizarre. Um, I'm gonna call that swap for now. It's doing more than just that, but um, I want this to be an array of 4 characters, is what I want it to be. And then I'm not sure what the types of these should be here, to make it look right, is being called here with more complex variables. If I change this to be a 16 byte array, that does clean up this decompilation a little bit. And then if we do the same thing here, make this a character pointer, make this a character pointer. Um, doesn't clean that up, unfortunately. Yeah, it's making the decompilation look worse, but in some ways it's actually more clear than what it was doing. If I could get size annotations onto the character arrays, it would probably be helpful. But let's go back up to its caller, swap. It does oh, it's right there. Okay. And it's just being called by this function, which I believe we got to by Okay, one of these other functions. Don't need our cross references to be so big. All right. So we've got some buffer here, which we are initializing, and then we're assigning each element of that buffer based on the input XORed with some crazy math. Not some crazy math, but math that results in some crazy values, I should say. It is just that times n, which is silly. And then we swap around some values and maybe we return something. This particular function is called in three places on 240, and the return result is never used. So let's correct that, which does simplify things ever so slightly. Um, Character pointer. Where's our two being used? Right. So we have two character pointers. This is. I should really just go to all of the functions that call this and call them some weird initializer. But it would also be nice to set some more types on these so that it looks more correct. Um, this particular one looks like a character array of 6 bytes. And then we're doing each of those six. Oh, okay, that actually makes sense. And then this one must be of 14 bytes, not 10. Okay, okay, okay. I think we're starting to find things here. Let's go back. This one's 6. This one's only 4. This one should be 8. Okay, 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 okay. This is cool. Um, I'm getting that number from the do while there. Since we're only going to the ith element of those variables, we know exactly what their size is. So this is a character array of 4. Let's call that buff as well. This is going to be. Oop, I went to the wrong one there. Go here. I want to go up arrow on that. I thought. Where were we? All right, so we're here. I need to go to this function. Oh, I was clicking who calls the string destructor, I think. Um, okay, so this one's 6, this one's 4, this one's 8. Let's call it 8. Let's call it buff. Go back here. Go to this third one. This one should be 9. Cool. This one is OXF. We've got, oh, forgot to name that buff. This next one's gonna be, I'm on the string destructor again. This next one is D, then 3. Sorry, that one's D, then 3. Yep. Y car buff 3. All right. And then we only have a couple more places here. I click the right one. We've got 16, 11, and E. car buff. This one's 16. This one is 11. We already have, no, we don't already have that. It's upgrading it to the larger integer type. So character 11. There we go. And now you can't double click these because that'll bring you to their targets. You have to hit up on them to get to the actual function. Then this one is E, character buffer of size OXE. And then lastly, we've got this one here, which is a character buff of 15. All right. So we have some of our types set. Um, Interesting notation there. Dot O. I forget if that's a size of that should be 16. Yeah, that should be 16, I believe. Maybe 10, but I'm pretty sure 16. Okay. So we're writing each element of that buffer. I should give all these functions names. I have to hit that. Oh, which didn't navigate me on the left. Okay. On the right, I mean to say. So this one is, and who calls all of these actually? So all of these are called here, which get called by other function. Oh, are these called period? Wait. So this one is called by something in a subtree that isn't called by anything else, which is neat. Always love to see that. Oh no, I'm navigating to the wrong thing again, aren't I? Click here, click here. We're in this function. Okay, yeah, there we go. Okay, so that's not called by anything. This one is called by something which is called by a init. This one is called by something which is called by a init. This one also called by something which is called by something. Don't follow the arrows manually, just click them, hit up arrow, which is called by main. Um, Keyboard navigation in the graph view is super useful because sometimes it's visually indistinct whether that arrow is going straight up or to the left. But by hitting left arrow and right arrow, we can see where it's going. Um, okay, and then this one's also not called by anything, but it calls string move. Okay. Um, so I still want to go through here. We can actually just pin these cross references is probably the better way to do this. And then we can go through each of these and say, okay, this function, um, weird off stuff. One, um, oh, I did the type. Um, Okay, so we'll call that number one. We'll call this number two. And it's just down arrow, enter. This one's going to be three. And I'll just go through and rename these so that when we see them later being called by functions we are reversing, we can immediately know that it is just one of these weird ones. We've already reversed. We have a sense of what it's doing. We throw it in the debugger if we wanted to know what the values actually become. But statically, we kind of don't care for now. I keep hitting Y for some reason today. 6, 7, and then I didn't mean to do that. I apologize. And then we can do 8. And then we can do 9. We could call it A. Let's keep them as decimal. 11. This one's going to be 12. And then we have 13 of them. That is quite a number. All right. We also might be getting rabbit holed by something that in the end doesn't matter. So let's take a step up. Um, Init weird buff. This one's called in a couple of places. Um, well, this is interesting. This is an instance actually where we can see the string it's getting. It's passing it to, we know that this is a character array of at least how many? 14? All right. Or I guess we can call that dest. And then we've got, okay, so this is an interesting case where we see the value being copied into dest directly. We see it being passed into this, which should initialize this buffer, and then it's moving it to arg1, which is strange. That is juggling it so much. But we've got this. This should decrypt it and then put it in the parent string. Um, you know, if we could fully reverse this, I believe we'd have to go to specify a function that decrypts a string. So we can probably decrypt these strings statically if we want to. Um, so we might do that. But it is interesting just to see these values and then it's getting returned here. Are these only called in one place, has no actual return value? Okay, and where is this that's being called? It's being called here, which is being called by, oh, it is getting called. It's just being called through a vtable. Fun. Okay. So we are finding um potentially a member of a bunch of different or potentially the members of a bunch of different classes that might all inherit from each other. Okay, let's get back up to main though. Um, Try to reorient ourselves. Okay, we were in a knit. Um, we found this decrypt and a knit string, which calls that weird one. Um, we see That string then gets destructed after we pull a value out of it. We then, oh right, I did want to see this side here. So we either move, oh interesting, okay. So if RAX3 is 0, presumably if we're able to get that environment variable, um, we set it to this thing, otherwise we copy what the environment variable was. Okay, so we either copy it from the environment variable or we initialize it brand new. This is the only place that this gets called. And in this instance, oh, we know that WeirdBuff13 is working with an array of 4, and it looks like we have 4 here. So let's make this a buffer of 4. And now this is going to be, we can actually now run through that decryption if we'd like to, because we see, again, some static values. We know each byte of the XOR key, so we could figure this out if we want. I'm still not too interested in it, in what the actual concrete value is. So I can move on from this for now, but getting, this is just initializing the string. So name init, if not existing, env, I'm going to call that. And what it initializes to, we don't know, but we can figure it out later. Then we're going to maybe create a directory with that as the name. Perhaps this is the current working directory. Perhaps it's trying to obfuscate its storage somewhere into the system. That bit's unclear to me. We also completely ignored whatever this function is doing, which looks to be nonsense, but it is initializing those 3 data buffers we saw. Let's name these. Are those the 3 that are being used? Those are the 3 that are being used. They're being initialized with this value of hex 2000, but I don't believe that's 2000 bytes right there. It is still only 100 and change in hex. Um, plus 18, plus 18. So these are all accessing also a fixed member of those buffers. So there could be other variables there. It could be a structure. Let's create them as structures maybe. Um, because it's giving the 18th byte of that argument plus or with that. So then we're dereferencing the 18th byte there. We're passing it to this function. We're ORing them. This result, we dereference the result of that OR. Um, and that's going to be 2000. So we're just ORing a byte. Yeah, let's name this by the way. Um, A or B. Oh, we can actually do A or B. And then we can, is this function pure? This function is pure. I'll call this A. I'll call that B. All right. So A or B. 0 extending them both to a quad word. It is expecting them to be 4-byte numbers. It's not characters, is what I was checking. Um, and then we and it. We set the is the return result of this being used. The return result of this is being used by this, which is not being used. Okay. So this doesn't have a return value. Um, which means this doesn't have a return value. I keep clicking. I want to click that, hit Y, hit void. All right. So then that maybe makes a little more sense. We're setting arg1 to be, yeah, that's a pointer to something. So this is still just A or B. So let's name it as such, A or B. Maybe dereference of A or B. All right, I'm happy with that. And then this is going to be, um, oh, you know what we can also do actually? Let's inline this. So if we edit the function properties, this particular one, um, let's inline. These two options here are going to be whether we're doing context sensitive analysis or context insensitive analysis. For this case, and what that means is that effectively the analysis data for a function in context insensitive analysis, you only have one set of analysis data for that function. And every function that calls that function with different arguments, with different values, of course, though all those calls are going to contribute to the analysis of that singular function. When you inline the address of when you're doing context sensitive analysis, you're bringing in that context to the analysis of that function. So you're effectively inlining it at every place that it's called, but then instead of reusing the analysis you got from like the group consensus, you're specializing it for that call site. So you get different results. Usually, call sensitive analysis, it will give you more precise results at the cost of performance. But sometimes we can do context insensitive analyses and get just as precise information. Right now, I'm just going to do it the way that I said I'll do it, and we're going to inline this one as well. Edit function properties, because it might be, I want it to, it might propagate values through the different it in fact likely propagates the values through the different calls of the functions when you inline it the top way. But no one has actually explained that to me yet. And now we can see this function is now very simplified. We're simply setting this field of a structure to be or equal to arg2. And in fact, we know that for all calls to this function, arg2 will always be hex 2000. So let's even go in and annotate that. RDI, I guess. Oh, there's R2. Cool. We can do say user variable value, constant value, hex 2000. All right. And now when we go up to decompilation, it'll show us exactly that. So now this is um didn't finish that. Struct field or hex 2000. And strictly speaking, it's or equals. All right. So we have not just some buffers then, we almost certainly have some structs. Why we're XOR equaling those fields to 0, or to, sorry, or equaling those fields with hex 2000 is beyond me currently, but I'm sure we will figure some aspects of this out. Also looks like these buffers aren't being referenced by anything else in the binary yet. But again, if they're structures or potentially all part of the same structure, we might not be seeing those direct references yet. Um, so yeah, let's leave that as it is. Um, Still bizarre, but we don't yet see the side effects of it. We'll come back to it when we do. Um, and then I was very curious about this function here. Uh, so this is after we reinitialize the string. Is this a copy? This function not called anywhere. We've got the value of the string. We've got no. So this is the only place that calls this. So this is the dir name. And arg2 is the old ret val. We have a new ret val for the new string that we are. Well, this seems pointless. Returns its own argument. So we definitely want to inline this one. Edit function properties. This time we'll do it context insensitive, um, which just removed that function call now from our list here. If we look at this, this looks like we're initializing the string and splitting the components. I imagine we're getting rid of some of the components there. Um, Split components of that. We have this function, which is only called in one location, doesn't have a return value, but it's already void. We've got the first argument dir name, second argument the components of retval. So this is going to be dir name. We do know that that is a no, that's not a string. It's a car star. So let's change that as well. What did that change? Okay, just change the size of the access there. And then we have arg2, which we know is that components of retval. Um, Components. So if the and I have no idea what this type is supposed to be at this point. I'm also realizing I don't think we've recovered all the um yeah, okay, we were missing an argument there. Just one though, right? Split components, RSI, RDI, maybe EDX as well. Okay, cool. So I think we're probably getting the second component from this and putting it in here. Um, Maybe that's a string pointer or character pointer of some sort. Um, or star that as well. And now it's only using arg1 though. And I don't like how that's a double reference. Unless, of course, this is also missing, or one of these are missing parameters. Yeah, neither of these think they take parameters. But if we drop down to the assembly, we can see this one kind of only looks like it takes. Oh, there's a whole function call in here being eliminated because we told it to inline this function. Because this is one of the weird things it's trying to trick us up on. Is this messing up the argument detection though? Because it returns its first argument. It could be. Because this one should have two arguments. Yeah. And then this call here and this call here both at least have one. Um, I'll just make them all void stars for now. But it also might be using the previously set up arguments. Um, for RSI. So if we guess that, does it look better or does it look worse? Always guess and check. I'm going to say no for that one. And oh, when I change split components to take a void star, it now wraps the return value to the list. And I really feel like no. Okay, interesting. And then we have okay, so I'm not sure this takes three arguments, but it certainly looks like it takes at least two, and I'm sure that this third one is trickling through somehow. Um, but I think it's safe to say at this point that we know that this function is just splitting the components and grabbing one of them. Um, I just wanted to make sure at this level that these arguments are being used. We didn't actually see this two being used, but it almost certainly is. Which begs the question, okay, no, this one looks like it is getting the two parameters. If I say it maybe has a third, it then grabs the return result from split components. But yeah, I think that one's wrong, which might actually mean that this one's wrong. But I think this one's right. And then this looks right to me too. So then we have split components. We're grabbing the second component. Um, and then this is probably the base path. And I have to imagine that this is a join. If string components equals dir name, return. Otherwise, we're on this function. which calls a lot of is local data lengths, capacities, copying specifically into arg1. We're doing we're doing things to arg2, particularly this thing, that thing. Um, I'm not gonna reverse this too much now and just call this whole thing join. Um, all right. And let's add a question mark over that because I certainly did not reverse that enough to know that it's join. And then I also think that this is not dir name, but base path. And that's something we can propagate up. So then this is going to be constructing a new, yes, this is constructing a new um, file name based off of a base path in an old file name. Um, there's a kind of join as well. All right, so who calls this join? It's only called by init. We're passing, okay, this might be beginning to make sense. We've got some base path here. If we have an environment variable that says what file we want to use, we're going to use that file. Otherwise, we'll use some default file. This base path certainly has other functions that interact with it. Um, it's setting the current path to eventually be that after we create the directory. So this is, what do you call this? I'm forgetting the name of that Linux command. I never have to use it. But when you create a directory and you make that your working directory, I guess just set cwd. But it's like a virtual, I think it's creating a virtual, not a whole virtual file system, but it's getting itself its own, I guess, temp directory. So maybe that's what we call it. Just create temp dir, create working dir. Let's call it that. All right. So there we go. Um, a lot of effort to figure that out, but worth it. It makes sense that now at the top of our main, we're creating some working directory that we go into. I suspect we're going to be dealing a lot with files here, which does not sound fun. But I'm going to take a quick break. I got to refill this water, and we will continue with this afterwards. So I'll be right back. All right, so we finished reversing the first function. Let's save. Here we go. And now we can look into this second function. I do believe this is going to be a constructor of some sort of some 8-byte type. So let's just, since I'm making some assumptions, let's go ahead and do it. Glad to see we have a bunch of system types. Let's create a new structure. This is going to be, let's just call it struct1, give it 8 bytes. All right. This first thing is going to be, we're going to apply that type, struct1, uh, and then let's name this struct1, struct1. And yes, maybe we should create that as a class instead, but that's fine. We have to create a working directory, struct1. Um, let's call this is going to take a struct1 pointer, and it's going to be called this. And what we do is we call operator new. Do we use the return result of this? We don't use the return result of this function. And it is not called anywhere else. So we're going to remove the return result from here. Simplify the code ever so slightly. Um, we create a new thing of 8 bytes. We initialize it to 0. We pass it to this, which passes it to this vtable for command. So this is structure exit command, I believe, which is inheriting from command. So let's call this command, which gets called by a bunch of people. The constructor for exit command, we've got it called by, let's pin our cross references again. By default now, we do pinned cross references. So if you just hit X on something, it'll pop that up. So this is exit command, exit command. This is create command. This is rename command. So all these, it looks like all of these are classes. Yeah, command is a class, and then all of these inherit from the base class command, which makes sense. So then we've got rename command. We've got print command. Oops. Oh, I'm in the type screen again. We have delete command. Interesting. It's interesting that these were all made into classes. I wonder, and it doesn't look like they have much other values either, since they're just a structure of a class of 8 bytes, which is effectively just its vtable. Um, delete command. This is edit command. Not implemented. Interesting. And then we have command. Okay. or compressed command. Yeah, compressed command. Sweet. Save all that. This is getting called by this. So this is almost certainly this. And if we want to, we go ahead and create all the types we have. Change this type. Let's copy it. I believe that all of these are 8 bytes. Um, so we do this. We have the syntax for an empty, oops, class. Um, and then we're going to do all these different command types. Naturally doesn't like to be copied out. All right. I can grab it from here. If we do, there's a data only view. Must not be, yeah, must not be here. Must only be in, yeah, assembly has a way to only show certain things, but we're, okay, we can just grab this, do this, copy that out, paste it over here. Ah, okay. We'll do it manually. We have our compress command, not implemented command, edit command, delete command, print command. We have our rename command, our create command, exit command, and that should be it. Okay, cool. So we have all our commands now. I can make classes of them. AI, what were you about to do? I think I liked that. It's not, it's shy now, but it was about to do it for us, I think. There we go. All right, so let's create all these classes. Create new types from C-source, paste all these in, hit create, and now we have all of our classes. I don't need this struct one anymore. I do want to see where it was being used so I can give it the right structure now. It's being used in this struct one thing I called, which we learned is actually exit command. Oh, interesting that we construct our exit command first. Perhaps that means nothing. Perhaps it does mean something. But the type of this is now exit command, and this is going to be like so. Oh, and the name of that, my bad. Exit command, exit command. Okay, so we create our exit command first. We're going to create, okay, this does not look like the constructor for another variable. But this is our create command. Um, this is called in one place. It doesn't have a return value. So we'll call this it returns nothing. Um, it's called create command, and it takes a pointer to a create command object called this. I think by default this dialog needs to be wider. Um, Create command, cool. Error specify parsing type. The type parser really doesn't like anything C++ specific. Gotta wrap it in backticks. But that looks great. All right. So then we have our create command, we have our exit command. It looks like it gets passed to functions. Is this the deconstructor? No. Well, maybe, but not obviously. And it looks like we have more functions that return arg1. So more weird stuff going on. But we are starting to actually make some headway here. This next one is going to be a rename command. Um, rename command, rename command takes this pointer. Perfect. Now we can keep going down, saving it every now and again. This is going to be the print command. I'll hit Y down arrow so I can just reuse all this stuff I was doing before. We can't just scroll to the last one, so I'll go back to main. I'll go to this next one. And again, it's helpful here that's following this really strict pattern of initializer, a function with two arguments, and then another function that takes the thing we just created. So we have this print command here, and now the next one I believe is going to be here. We've got this one's the delete command. All right. So this, I say to people all the time, if you start reading from the top of a binary and you start reading down, you're doing something wrong. And in this particular case, we definitely got rabbit holed for a while on this create working directory thing. I got caught up on some of the stuff at the top when I could have just looked at the bottom that we're creating a path and we're setting our current path. And I probably never would have had to reverse any of this. It was fun. But as soon as I got past that, I'm able to start making significantly more headway on the binary by looking into some of these other um, functions, which eventually contain hints to symbols that we were able to extrapolate to the rest of these classes. But let's just keep going here. This is the edit command. All right, that didn't stick. Although technically that is the correct. Oh, interesting. That's wrong though. I guess I will need to go through and correct those as well. I like how that got cleaned up there. Looks good. Um, all right, cool. And let's call that edit command. Once we do all this, I'm gonna just go back through and double check everything. This is the not implemented command, Y down arrow, not implemented. Um, compress command. All right. And then I think we have Maybe one last one? Or no, actually, that should be it. Um, this type is still being referenced in a couple locations. I don't think I propagated my type information enough. Here we go. So yeah, I still called that one that. This needs to be an exit command. All right, cool. And then this is also that same type signature. So we're going to go through now and we'll get, I'm going to close that left sidebar. I'm going to switch away from Tonto. I haven't been using it for a little bit. Go back into linear here. Go back to main. And then I want to desync this right tab, no sync group. So I can go to exit command. This one's fine. I could go through here if I want to and set the type of this. We might need to come back to those functions, we'll see. But I want to see this one. Oops, I hit H by mistake. Um, ah, okay, that was the wrong one. I want to go to this one. Yes, okay. So this one has the type. I can hit Y on this function, copy it, and I just want to apply it to this because it thinks it's taking some vtable type because it's immediately overwriting stuff with vtables. But I want to tell it that it is the parent class and not the vtable, the internal vtable thing. All right. I'm guessing the second one again. Yeah, okay. So oops, Y, copy, and Y, paste. Okay, so now we can go to the print command. This here is void, and it is a print command. Oh, called this. Copy and pasting was definitely easier. All right, and then we've got delete command, copy, copy, and paste. Edit command, Y, paste, perfect. Then we're near the end. Grab the type from here, set the type of this function. Then we can grab the compress command. Do we have two not implemented commands? Did I do that wrong? So we've got not implemented, which goes to not implemented, which goes to the base command. And then the second not implemented, also the base command. I did something wrong here. Not implemented goes to not implemented, which goes to not implemented. So this is the real not implemented. And then this one, oh, they are both not implemented. Bizarre. Let's open up Tonto again. And if we go back to main, we can see, okay, this not implemented. Tonto occasionally loses its ability to focus, much like reverse engineers. Full call graph. There we go. And now, okay. Let's just close this BNDB and come back. This is going to be the full call graph. All right. So we have not implemented here, which looks a little like this, calls into this function, which has the vtable for command. I kind of think, no, this is the vtable for not implemented. And then we go here, also vtable for not implemented. Is it the same vtable for not implemented, or are there two tables for this? Um, so this is A68, and this one is A68. Okay. Those must be the same then. It's just weird they did it twice. Yeah, that's all. Okay. That's okay though. Maybe it was a bug of theirs instead of a bug of mine. That really does remove a lot of code when you do that. Perhaps that other type is more correct. Hard to say though. This command function should definitely be taking a command structure. Did I not make the command structure? I did not make a command structure. I very nearly clicked stop broadcasting. Um, it is just to the left over here. Um, Cross references to this structure, there are none anymore. So we can undefine that type and we can make our command. Create a new structure called command. Let's also call it 8 bytes. And now this should be taking a command pointer. Interesting. So now instead of overwriting its first argument, we load the effective address of that and we move it into, yeah, that should be right. Um, this function also doesn't have a return value. And that doesn't look right. Is that base function marked as pure? Or I like this. arg1 equals that. But then as soon as we go up to high level IL, I think that's gone. Because this does need to be a double pointer, maybe. Unless it's like, can we even do this? Oh, we can. Okay, but it doesn't change that. I don't know if I have the type on this wrong or not. I'll have to kick this over to someone who's a little more versed in C++. Reversing. That is curious though. Okay. So what we were doing though is we were looking at these and making sure that we had all the subtypes correct. So this one looks right. Um, Even with that weird internal command thing, we're not seeing um, the vtables being copied anymore, possibly because I have the wrong types. If we look at this, this is... Are we missing anything else here? No, it really is just... And that's on the stack. I don't think there's a way... Oh, how are these being used otherwise? We don't. We just see these couple of functions happening, getting some input, doing nothing with it. um, and then what if these functions are? So maybe these are pointers to all these elements. If we change just this first one, and I propagate, forward propagate variable type, then instead of a pointer, it's a double pointer. And this is this also a double pointer? What's this doing? Oh boy, one of our fun little functions again that does nothing. Okay, we have a bunch of things to inline here. Oh wait, no, this does do something. arg1, dereference of arg1 is 0. So this is not pure, because there are side effects, but we can inline this, and it's at the bottom of a chain. This now looks like that. If we inline this, and then we go here, and we inline this. I mean to be doing this top one. I think I did the bottom one on the last one. And then we go here, arg1 equals 0, and then we've got this thing, which is itself an obnoxious chain of functions, which just returns itself. And this one is pure. Can I inline? Is there an action for doing this inline preserving instruction addresses? This is also 230, which is this one over here. Inline 3. Okay, that needs to be an action. I do believe that we can do a current function dot inline during analysis. It is, what is the type of that? I want to set that just to true. It looks like that worked. So inline this one, and now inline this one, and now inline this one. And we can see this gets called in 3 places. Including whatever this is, which is called my main. This is the sub 2C0, 2C0. Okay, so this is this thing. What it's doing, and this is all still now assuming that these are pointers to these classes instead of the classes themselves. So we're still just trying to see if this logic maps out to be correct, that it's a pointer and not just an 8-byte element. But then my question is, so is it allocating a new pointer or is the structure 8 bytes? Um, and I kind of think the answer is that this is a command double pointer again. We're setting, and if I hit Q on that, this becomes, this gets the wrong type, so I didn't want to do that. So maybe this is an exit command double pointer. Also, this should be this. Um, so exit command, we're allocating a new buffer for a pointer in theory. And then let's forward propagate this type. This should also be named this. And now the dereference of this equals the um, address of that. So now it makes sense because, um, yeah, and now it looks correct. Okay, cool. So they're all weird double pointers. Because of course they are. Makes more sense than them all just being these weird 8-byte structures with nothing in them. But the fact that I didn't see calls to new originally is, oh, I get it now. Okay. So, yeah, we do declare the pointer here, but then we're just actually creating them on the stack inside the um, initializers, and then we're actually populating those data inside the internal initializer. That's a weird way to do it in my mind, but why not? It works out, and all these values make a little bit more sense that way too. So this is going to be our new structure. This function took that name there. Who calls you? Only exit calls you, and you're one of these annoying functions again. So let's inline you during analysis, and inline you during analysis, and inline you during analysis until we get to this awfulness here, where are all our types correct? We have this is the outer exit command. Yes, this is the outer exit command. It takes a this double pointer to an exit command. It creates a new double pointer, which it passes to the internal exit command. It dereferences that double pointer and gives it new, and assigns new pointers in there. And then we create a new structure. We go down to medium level IL. We can see artifacts of all the inlining we did. But it creates this new structure from it gets multiple pointers to the new structure, multiple pointers to the old structure. Wait, no, this is the new one. This one's the old one. New being relative, of course. So we have this is interesting, but a little bit painful to wrap your head around. Um, we get the old and new again. Huh. So it is certainly just moving data around a lot. I would want to walk through the medium level IL for this a little bit more carefully, rename all the structures to think about what it's doing. But we got here because we were worried about the different types. Um, oh, that certainly should not be correct. Oh no, it is. It re-clears the this and just resets it to whatever it was. So I think this might all just be obfuscations as well, which is why it's weird. I think here we've gotten to what this is actually doing at this point. Um, just with some potential extra moves, hopefully not through the data section, as well. But I'm comfortable with that for now. I do want to fix my mistakes. If I do asterisk on this, does not turn it into a pointer. If I search for pointer, if I search for pointer, follow pointer, run pointer sweep, I don't know that I've heard of pointer sweep before. Oh, that must be, I think that might be for Firmware Ninja, potentially. Looking for pointers. We've got print command, we've got delete command, edit command. Not implemented. Press and not implemented a second time for some reason. Okay. Um, and then all of these functions really take double pointers, which makes the decompilation in theory look better at this level, but I'm not sure if that's anything we need to worry about at the moment. So I'll leave it like that. I will just finish these last couple. Yeah, okay. And then we have not implemented again. which does not yet have the right type. Cool. And this is another one of those weird chains. We got a lot of weird chains going on there. Okay. Lastly, it looks like we might have the generic command. Oh, no, this is not implemented command. But then we reassign it. Does that need to be? You can take this out now. Um, okay, it thinks it takes no arguments. If we say that it takes two arguments, what does that look like? That looks wrong. That looks potentially right. But likely not three arguments, just the two. Oh, maybe just the one. You know, it's hard to say which way. I think it might be this way, in which case are these... No, we said that these aren't returning anything unless we're missing arguments to something else. That certainly wasn't right. And that's not right. So I think we're good. Um, just for giggles, what is that? Um, no, okay, I don't think that's correct either. I do think that this might be the current command here. It would make sense in having a double not implemented command, but just initializing it to start as a not implemented command. So we have the command pointer, yeah, command pointer, which we start as not implemented. Um, and then presumably we change that current command to be all the other ones. We're just starting it as not implemented. Oh, menu command. It's a menu command. Interesting. Um, we don't have a structure for that yet. Okay. Let's see though. We've been going for 3 hours. Only got a couple of you guys left. I am curious to keep pushing this forward, but we'll probably stop soon. I just really want to look into like these two functions, I think. This one calls a bunch of functions. We can see on the right here, it calls a lot of functions actually. And then what's this one at the bottom? Looks like one we could probably inline. Um, Also looks like it almost certainly has the right type, the wrong types. So let's not do that for now. Um, until we can give it the right types. But it's being called by this. Oh, interesting. And now we get back to our weird buff stuff. So we've got this 40, E40, E40 there, which takes a result in the buffer. Result, remind me, we think is a number. Where does this function get called? Gets called in several places where it thinks there are two return values. I suspect that could be false unless it is returning a 16-byte array, which is more likely. The argument of this function is, or the what it's operating over is a 16-byte array. So it returning a 16-byte array could make sense if I tell it that. Um, does it look more correct where it's being called? No. And if I tell it instead that it's an array, a character array of 16, um, and this is a character array of 16, it still doesn't like that. But if I call this a character array of 16, it understands what's happening. So I do think that's correct. Even though it would be nice if we could clean that up. I do believe with the incoming calling convention changes, that might be the case. I heard him specifically talking about um, multiple returns for structures and arrays of conveniently eight register aligned sizes, let's say. Um, okay. So it was this function here. Ah, that just happens to be at the bottom of our big thing here. I just wanted to see, okay, so that is a character pointer. That's also going to be a character pointer. Let's update them over here. Car star and car star. And what did that do? Exactly nothing. Um, is the return result from this function used? The return result from this function is not used, so it's definitely not a 512. And then we can see, is it really just from the stack into ZMM into, sorry, XMM, and from XMM back into arg2 or back into arg1? Okay, I think that's what it's actually doing. Let's inline this now. Um, I don't know why we would want to overwrite arg to arg1 with arg2, but like, yeah, overwrite arg1, arg2. Now it's inlined in here. I believe it was being called down here, and it doesn't look nice. We have our two buffers. This buffer is not declared in medium level IL, but it is a 10-byte array. We have we're going through each element of that and we're setting them, and then at the end of the function, we're copying that 10 byte array onto the stack. We're copying that also onto the stack again. Immediately after it. So we're effectively duplicating that buffer. Um, yep, here we were. Which is what this is saying, I think. Kind of. Yeah, I think we're copying the 16 bytes from here to here, then we're copying the 16 bytes immediately after it. So this is effectively turning into a character array of 20. That looks more accurate to me. Except, why do we still have R3? Or 34, 38, I should say. I don't want it. Did I not make that big enough? Wait, we have buff over here with a size of 10. I have buff in here. Okay, I don't know what happened. That was weird. Okay. But now it looks like, where's buff 1? Who is buff 1? Who is she? Um, okay, it's a register. I guess we could have seen that by going over here. Um, yeah, buff 1 is a 20 byte character array. I think buff 1 is a 10 byte character array. But then on the stack here, buff is a 20 byte character array. Okay. And potentially 30, 40. Hard to say. So then R1, not there right now. We're down here. We're still looking at this. Um, if I inlined this edit function properties like this and go back, I'm still seeing these go-tos, but it doesn't annotate that it's within a different function. So it looks a little bit cleaner, I think, if I annotate it as not a um, whatever I was saying. Got distracted. Okay. Oh yeah, as not context sensitive. If it doesn't really matter though. We still have this buff one register being copied 16 bytes from buffer, and then the second 16 bytes. It's so weird. It's just duplicating itself, I think. Oh, and now we're actually taking portions of it. We're taking the second half of buff. This has to be an obfuscation. But we're not doing anything with RDX. So maybe it's just bad compiler optimization. Or if we go down even lower, it's not Benja being weird. So it's hard to say in this case. Yeah, it's showing that it's showing the read into that place in the buffer, but it's just not doing anything with it. Is it doing anything with RAX5? That's what it's returning. Well, everything returns RAX. But in this case, we actually are. We're returning that 10-byte character array. All right. Um, so I guess the result of this is ignore the weirdness, and really the meat of what's going on is in here, where it's transforming every character of the input. Um, but let's see, we got there because we were looking at this thing, which is one of the functions called by main towards the end. Um, I click it and hit up arrow, we get to main. Believe it was it this one? It was this one. Let's forward propagate this type. Oops. Cool. Oh, why does current command not have a command pointer type? Q? That's okay. Command pointer. It thinks it's a 4-byte number though. Concerning. Does not appear to be using its arguments. I am reversing a C++ binary right now, which has no symbols. I'm answering the question in chat. That so far what we've been able to recover is there's this initialization function at the top, which creates a directory and sets our current path into it, with a whole bunch of weirdness in between. Um, we had to reverse a little bit some of the C standard library functions, I think, and we found like weird wrappers to destructures and stuff, but it's controlling what directory we're creating and entering by some environment variable. I assume it has some default path there. And then after that, we have just a whole bunch of different command initializations. And we were able to recover each of these different classes, because I'll open a raw version of this. This is what it looked like before. And we saw this weird pattern of declaring a variable, passing it to a function, passing it to a function that takes two arguments, passing it to a third, and then again. So each of those we were able to identify as different commands on our stack. Looks like we have some more variables there we haven't yet gone through yet. Potentially more commands. All these things it looks like. Not sure what these are yet. Um, but the way we were able to find that, I accidentally just closed that, was in here. Um, Weird pointer stuff is going on, but then we're assigning the base of that pointer to be the V table for the different quote unquote commands we found. Um, so I believe we've seen all these commands and we've created all their structures in the version we've been working on. We've had to correct a couple things because originally I thought maybe the structures themselves were 8.8 bytes, but it turns out that um, it's a double pointer. It's a that pointer on our stack, a location on our stack is a pointer to the type. So we're passing a double pointer here, and then we're creating um, new memory to put a new pointer in, which is what we're returning. It's doing some weird stuff. A lot of structures on the heap with references to them on the stack. Double pointers are always interesting to work through. But it seems like it creates all those commands, and then at the bottom, creates a generic command, the base class pointer, initializes it to not implemented. And now we're at the bottom here of, okay, what's actually going on? We have our current command. Um, we give it the vtable of menu command, which is not a class we've seen or a structure we've created yet. And then what's going on in here? And I think that I got what I did was I got here and I was like, oh, okay. So this function calls all of these functions. And at the bottom, I found a function we were looking at earlier in the stream, which does some really weird. We have a buffer here, which we're iterating through 1 byte at a time. I guess this should be 10, but later it's used as a hex 20 byte array. But we're iterating through all, yeah, we're iterating through, oops, there we go. We're iterating through each element of the buffer and we're XORing it with something that's coming from an argument, and then also this really awful math, which we determined is just this constant times m. Yes, this is cybersecurity. This is reversing. Um, we have an application that we don't know what it does, and we're trying to figure it out. Um, so far, kind of all we know is that it's in C++. It's got commands. It's using constructors and deconstructors. Um, and Binary Ninja is letting us turn the raw bytes of that file back into decompilation that we're um, recovering types for. We're creating those types. We don't know what all the fields of those types are yet, so we think they're 8 bytes. Maybe they contain pointers. Maybe they contain two 4 byte numbers. Whatever it is. Um, and yeah, we're just trying to figure out what it's doing. What doing? And down here again is probably like we have all the initialization of this program. You can see that this is the main function. We know at least the main function. We have symbols for we have symbols for very few of the functions. There's a lot of functions in here that we have yet to analyze to figure out what they're doing, but they're calling functions we've already looked at. So I think that this one here is string move, std string move, that is. This is another one of those weird buffer functions. We were finding that this function is duplicated throughout the binary with different hard-coded values in here for different buffer lengths. Um, and this was a CTF binary. So this is doing something. And I think there is a value in here that we can extract as the flag. Um, it's designed to be hacked. And then I believe over here is again where we're starting to get towards what's going on. How it's accepting the commands, how it's processing those commands. If you go back to the beginning of the stream, we had a different trainer for one of our class. We have a conference in a couple weeks, Reverse. We have third round is on sale. The room block is selling out, so you should get your tickets now and sign up for one of the classes if you find all of this interesting. I'm teaching more just the reversing stuff. We had Brandon on earlier in the stream who's teaching more of the firmware stuff. Um, so that's raw binaries that's running on like a camera, or he was showing in particular the Meshtastic devices, and they have firmware. So they're writing to different hardware devices, and then you can identify what those hardware devices are. It turns out one of them was a speaker, and then he also showed off some bugs he found as well. So lots of interesting stuff here. Um, okay, So right, we were here. I found this cluster of functions I wanted to analyze and got distracted again. And then we also have this function here, which is a little less complicated. We can see we're getting some input. Um, we're getting 10 bytes of input. Yeah, 10 bytes of input each time. This function is only called, we can see our cross references, so it's not called anywhere, so it doesn't actually have a return type. Since it's grayed out, Binary Ninja is not confident that it's in int64, so we can just override it to avoid. We know that um, RAX is usually the return value from functions in the assembly, so everything technically returns a 64-bit number, but it's not being used, so we can just set it to void, and it cleans up the decompilation a little bit. Instead of saying it, thinking it returns 0, it just doesn't show a return value. So we're getting some input here. We're getting 10 bytes of input, and where is that input being placed? If I give this a second argument, it says var 14. If I give it a third argument, it has to create something. So that's wrong. So I think that this definitely takes two parameters. Um, var 14's on our stack over here. We have up to 10, we have 10 bytes, or we have 12, I guess. Um, let's create this as a character array of 10. But it's really only setting 4 of those bytes. And then I made everything look worse down here. There's actually not that much space. Oh no, there is. It's just that where is it storing that? Yeah, okay, it's storing the stack canary in var10 there. Okay, so it is only 4 bytes. I can set it to a character array of 4 bytes if I want. Does that help anything though? No, that doesn't really help this decompilation look good. Um, RSI1, I don't think that this is correct either. And then RDX, yeah, that also doesn't look correct. So I think that takes one argument, returns one argument. It's just getting 10 bytes of input. I cannot tell what it's doing with that input, except maybe to put it in var14, which doesn't seem to be. What if this has arguments? Oops. Y int arg1. That does not seem to help things. So guess and check's a valid strategy. If you do something and it makes the decompilation look worse or not better, that's often a hint that you're not doing it right, that you did something wrong. Um, okay, so maybe this is like flush, um, or get 10 bytes. I've had my stack in. Um, so, all right, that's something weird. It could make sense at the end of each loop. Let's go back to main here. To be, oh, I messed that type up. Oh, Previously, it had looked like this. But if I say that the return of this is void, okay, so now it's rather insistent that there's a return type for this. Ah, okay, that makes sense. Maybe this is get'nt. Okay, that makes a bit more sense. Zero extending that to a quad word. If I change this to a 64-bit number, no, it's definitely a 4-byte number. The main and okay, so zero extends that. That's not a big deal. Get in, but now this is our current command. Next command, or perhaps the result of the next command. All right. Well, I think I'll leave this off here for now. We can pick this up in the future if we would like to. But again, if you have not already gotten your tickets for Reverse, go grab those. Go get the room block before it's over. And yeah, Brandon's class is super exciting. He's going to be looking at a ton of stuff to do with firmware, more of the Meshtastic devices if you're curious about that. But otherwise, thank you. And of course, my class as well will be going over this stuff as well as how to automate a lot of this. There are a lot of patterns here that I've been very tempted to write different scripts for to help us do things maybe a little more quickly, to do it if we're going to be looking at C++ binaries again. But again, for now, I've been Kyle Martin. This has been another Binary Ninja stream. Thank you guys for sticking around, and I'll see you at Reverse.